In this video on gases, we will be looking at some quantitative things to do with gases and going through some gas calculations, both for the ideal gas law as well as Dalton's law of partial pressures. First thing you want to do is look at Dalton's law of partial pressures. And you can easily identify that you're dealing with a Dalton's law of partial pressures problem because you're pretty much only seeing pressure units. And you're seeing that sum of the parts is going to equal the total for pressure. So in this problem, it says a mixture of three gases has a total pressure of 9.9 atmospheres. The pressure of the neon is 34.2 psi, and the pressure of the argon is 800 torr. What is the pressure of the krypton? So right away, that should be screaming out loud, Dalton's law of partial pressure. I'm only seeing pressures, I'm seeing parts, I'm seeing a total. So I'm just going to put this in terms of our Dalton's law of partial pressures equation. The total pressure is going to equal the sum of the parts. In this case, the pressure of the neon, the pressure of the argon, and the pressure of the krypton. Next thing I'm going to do is I'm just going to pull things from the question or the word problem and get them into the equation. Pressure of the neon, 34.2 psi. Pressure of the argon, 800 torr. Pressure of the krypton, what we're looking for. Now that we have things on the word problem, we can actually start doing some manipulations. But before we can do any manipulations, we have to make sure that we're in a common pressure unit. Now, sometimes the problem will tell you what it wants the pressure unit to be that you report your final answer to. Other times it gives you a little bit more freedom. In this case, they don't say. It just says, what is the pressure of the krypton at the end? That means we have the freedom to pick whatever pressure unit we want to. In this case, I chose to pick atmospheres. Remember, sometimes they're going to force you to do it in a specific pressure unit, though. For this problem, I picked atmospheres, so our goal is to convert everything to atmospheres. Total pressure is already in atmospheres. I don't need to do anything for that. But the PSI, I need to first convert that into atmospheres. So that work's shown on the right-hand side, 34.2 psi. The conversion between psi and atmospheres, 1 atmosphere is 14.7 psi. So that's going to give us our 2.32 atmospheres. So that's where that came from. I'm going to do a similar process to convert the torr for the argon into atmospheres as well. So 800 torr, again a one-step conversion, 1 atmosphere 760 torr, and that's going to give us the pressure of the argon in units of atmospheres. So that's where the 1.05 came from. The pressure of the krypton, that's what we're looking for. Now that we're all in the same pressure unit, atmospheres, we can just make the sum of the parts equal the total. Here's our variable that we're looking for, the pressure of the krypton. We just need to isolate and solve for that. So subtract off the 2.32 and the 1.05 in order to isolate the pressure of the krypton, and we would get the pressure of the krypton to be 6.62 atmospheres. Dalton's law of partial pressures is real easy to go back and double check yourself for, because you know if the sum of the parts equal the total, it has to be right. If the sum of the parts don't equal the total, it has to be wrong. Those are the only two choices. So if we put the 6.62 atmospheres back in here, 6.62 plus the 1.05 plus the 2.32 does indeed equal the 9.99 atmospheres. So we feel really good that we did this problem correctly. Next, I want to do some ideal gas law problems with you, some PV equals nRT problems. So this problem says 70.4 grams of CO2 is placed into a rigid container with a volume of 15.7 liters and a temperature of negative 30 degrees Celsius. What will the pressure inside the container be in atmospheres? So we're looking at the ideal gas law here. And pretty much all ideal gas law problems are the same. There are 5 different things in the ideal gas law: pressure, volume, amount, R the constant, and then T. In any specific problem, you're either going to know or have access to those 4 of those 5 things, and then you're going to be asked to solve for that 5th part. What you might be solving for might be different in each case. So in this case, we're going to be solving for the pressure. But in other cases, maybe you'll be solving for the volume, or the N, or the T. But as long as you have 4 of the 5 pieces, you can always find that 5th piece. So let's kind of show that process for this one. I'm just going to get things where they go in the proper units. Pressure is what we're looking for. Volume, we need to have it in liters. Right from the problem, it tells us 15.7 liters, so we have the volume. N is the moles of the gas that we have. Right now we have it in grams. Remember, you just can't throw numbers into the ideal gas equation. That's a surefire way of getting every single one of them incorrect. Instead, you got to make sure they go in the proper units. So we have to do a little conversion. Same conversion we've been doing from very early on in the semester, gram to mole. 70.4 grams of CO2. Use the molar mass of CO2, which is 44 grams per mole, and we'll get 1.6 moles of carbon dioxide. So we have our moles. R is always provided to us, so that's where that came from. Lastly, we need the temperature in Kelvin. The conversion between Celsius and Kelvin is Celsius plus 273. So we get our negative 30 in here, and we'll get a temperature in Kelvin of 243. So that's 243 is where that temperature in the Kelvin came from. At this point, we look and we say, okay, do we have 4 of the 5 pieces? Well, we don't have pressure. That's going to be the one we're looking for. We have the volume. It's in the right unit. We have the moles. It's in the right unit. We have R in the right unit. And we have the temperature in the right unit. Now you're going to isolate and solve for the variable. So in order to isolate and solve for the variable, everything on the right-hand side we can multiply together, condense that down, combine all 3 of those terms, and then to solve for the pressure, we would divide by the volume, which is 15.7. So to isolate for the variable, in this case the pressure, multiply through everything on the right, then divide by 15.7, and we're going to get our final answer of 2.03 atmospheres. And all ideal gas problems are going to work the same way. You're going to have access to 4 of the 5 pieces. You're going to solve for that 5th piece. Key things, making sure you're using the correct units. Our next problems involve just combining what we just did with the ideal gas law and coupling it with stoichiometric principles and calculations that you've been doing from previous units and previous chapters. This is essentially gas stoichiometry, and it literally is just stoichiometry plus the ideal gas law. So if you're already pretty comfortable with stoichiometry and you can do the ideal gas law, these are going to be really, really straightforward calculations for you, because it's just combining the ideal gas law with things that you're already pretty comfortable in doing. So this question asks, what mass of strontium and how many milliliters of 3.5 molar HBr is needed to produce 46.3 liters of H2 gas at a pressure of 720 torr and a temperature of 25 degrees Celsius? And they gave us the equation here, but one thing we want to pay special attention to is make sure it's balanced. Remember, they may not give you a balanced equation. It's your responsibility to make sure that that's balanced. Kind of highlighted in red the 2 here as the coefficient in front of the HBr. That's really important to make sure that things are appropriately balanced for this. So in terms of doing gas stoichiometry problems, there's really 2 halves. There's the ideal gas law problem, and then there's the stoichiometry problem. And sometimes you have to go back and forth between them because they're related to each other. I think it's a good idea to start with the ideal gas law part of the problem and just see how far you can get. So ideal gas law, PV equals nRT. Just like we did in the previous problem, we need to kind of go through and get things from the problem into the proper units. So P, the pressure, that has to be in atmospheres. It's given to us as 720 torr. So we need to do a quick torr to atmosphere conversion. And again, that's a one-step process, 720 torr. 1 atmosphere is 760 torr. That's going to give us our 0.95 atmospheres for our pressure. Next up would be the volume. Volume comes right from the question. We can use that as is. So we took care of our pressure, we took care of our volume. And the moles of the gas, we don't know yet. That's going to end up being what we solve for in this. R is always given to us. That's the gas constant. And then T, the temperature in Kelvin. So a real quick Celsius to Kelvin conversion, 25 degrees Celsius is 298 Kelvin. So if I look here, I have the parts that I need. I have the pressure in atmospheres. I have the volume in liters. I'm looking for the moles. I have R and I have T. I have 4 of the 5 parts. I can solve for the 5th part, which in this case is going to be the moles of the H2 gas that end up getting produced here. So in order to solve this, you have to do some algebraic simplification and isolation. You got to isolate the variable, which is N. So in order to do that, you'd multiply the pressure and the volume together, and then you would divide by R and divide by T in order to get the N by itself. When you've done those algebraic steps, you'll see that you'll get 1.80 moles of that H2 gas. Well, that doesn't fully answer the question. That's how much moles of the H2 gas got produced. We want to know is how much starting material did we need? How much of the strontium and how much of the HBr did we need in order to achieve that? Well, at this point, it's really back to just flat out stoichiometry. We've handled all the gas parts to this. We just need to now go and deal with the stoichiometry parts. Remember, there's 2 questions here. What mass of strontium and what volume of HBr? Well, let's start with the strontium. So we need to make 1.8 moles of H2 gas. The molar relationship between H2 gas and the strontium is 1 to 1. So we have that part in our conversion. The moles of H2 gas would cancel. So we'd have moles of strontium. Well, moles of strontium, we want grams of strontium, so last step would be to use the molar mass of strontium, which is 87.6 grams per mole. Your moles of H2 would cancel out. Your moles of strontium would cancel out. The unit you're left with would be the unit you want, grams of strontium, and that would turn out to be 157.7 grams of strontium. We would do a similar procedure to figure out what volume of the HBr we would need as well. Again, starting with our moles of gas, 1.80 moles of H2. How does H2 relate to the HBr? Well, it's going to take 2 moles of HBr for every 1 mole of H2. From our balanced equation, we need to make sure we reflect that. That's the next step. Well, our moles of H2 would cancel out. We'd have moles of HBr. We want to know what volume at a specific concentration. So again, remember back to what we talked about before. Whenever you see that molarity, that capital M, rewrite what it really is. That many moles per 1 liter, and then use it as a conversion factor. So 3.5 moles of HBr for every liter. I want the moles of the HBr to cancel out. They do. Now I have liters. This question asks for it in milliliters instead of liters. So lastly, a quick milliliters to liters conversion, and we can determine what volume of that 3.5 molar HBr we actually need. So for our last gas problem is another kind of very classic stoichiometric problem. It's a limiting reactant problem. This problem asks what volume of gas can be prepared from a reaction of 28.5 grams of Na2S with 244 milliliters of 2.3 molar HCl at a temperature of 30 degrees Celsius and a pressure of 740. How do we know it's a limiting reactant problem? Well, we have finite amounts of each of our two reactants. So we have to figure out which one runs out first. Again, we need to have a balanced equation. Remember, don't assume it's balanced. Remember, you might have to balance an equation on your own. Kind of highlighted that in red. If this wasn't balanced, we'd have to make sure we got the proper coefficients in there. Again, I want to start and see how far you can get on the ideal gas law part of the equation first. So I'm just going to get things out of the word problem. Well, to use the ideal gas equation, I need pressure. Well, I need the pressure in atmospheres. It's in torr. So again, a quick torr to atmosphere conversion, 740 torr. 1 atmosphere is 760 torr. That's going to give us our 0.97 atmospheres. That takes care of our pressure. The volume is what we're looking for, so we can't do anything with that. N, I don't know anything about N yet either. I do know something about the R. R is provided. Okay. So we have that. The temperature is 30 degrees Celsius. Change that 30 degrees Celsius into 303 Kelvin using the conversion equation between Celsius and Kelvin. So I look where I'm at on the ideal gas equation. I have the pressure. I don't have the volume yet. I need to look for that. I don't have the moles. I do have R, and I do have the temperature. At this point, I can go no farther in the ideal gas equation. I can go no farther because I still have two variables. I don't know the volume and I don't know the moles. Until I figure out one of those, I'm kind of stuck on the ideal gas equation part of it. Until I can figure out the moles, I can't figure out the volume. Well, how can I go about figuring out the moles? Well, that's where the stoichiometry comes in. The gas is on the product side. I have finite quantities of my reactants. I need to do a little stoichiometry work just like we did in units 1 and units 2. First, determining what the limiting reactant is. That limiting reactant will determine how much of our product we will actually make. So we're going to do this the exact same way we did it before. Stoichiometry didn't change from when we did it earlier. In order to figure out what the limiting reagent is, we need both in moles. So I'm just going to do a quick gram to mole conversion for the sodium sulfide. 28.5 grams of sodium sulfide. The molar mass of sodium sulfide is 78 grams per mole. That's going to give us our amount of sodium sulfide, 0.365 moles. I'm going to do a similar process for the HCl. This is a solution, so I'm going to start with the milliliters. 244 milliliters, change it to liters, 1 liter, 1,000 milliliters. Then again, using that molarity, remember what that capital M means, that many moles per liter, 2.3 moles of HCl per 1 liter. Liters canceled, milliliters canceled. What am I going to have? Moles of HCl, 0.561 moles of HCl. At this point, when you have your two reactants in mole quantities, it's now time to determine which one's going to run out first. Remember the procedure that we went through in order to figure out what the limiting reactant is. We have to compare what we have. We have 0.365 moles of sodium sulfide, and we have 0.561 moles of HCl. We need to compare what we have to what we need. My balanced equation tells us that we need twice as much HCl as Na2S. Now we have to ask ourselves, when we compare Na2S and HCl, when we compare these two together, what's the relationship? Do we have twice as much HCl as Na2S? And when you compare this, 0.561 is less than twice the amount of 0.365. 0.561 is less than twice 0.365. So what that means is we don't have twice as much HCl as the Na2S. Being we don't have twice as much, that's going to make the HCl the limiting reactant. It's going to run out first. Everything's going to be based upon our limiting reactant. So that's what we're going to use. That's why determining that limiting reactant is such an important step. So our limiting reactant is the HCl. We have 0.561 moles of it. We want to know how much gas will that produce. Well, the relationship between the HCl and the H2 is 2 to 1. 2 moles of HCl are required to make 1 mole of the H2S. So that's going to tell us how many moles of H2S we can produce. That's going to be 0.281 moles of H2S. That's our gas. Remember why we went through and we solved that? We went through and we solved that because that was our missing piece from the ideal gas equation. We couldn't solve the volume part of the ideal gas equation because we didn't have the moles of gas. Well, that's why I went through this stoichiometry, so we could get this moles of gas right here. So we could get that fourth piece to the ideal gas equation. Now that we have the 4 pieces for the 5, I have pressure. I don't know the volume. I just solved for the moles. I had R from before. I had T from before. Now I have 4 of those 5 pieces. I can solve for the 5th. This time we're solving for the volume. So you need to combine terms and then isolate in order to solve for the variable, which is the volume. So in order to do that, you would multiply the 0.281, R, and the temperature all together, and then divide by the 0.97 atmospheres in order to isolate the volume. That's going to give you your volume of 7.21 liters. So when you're doing gas stoichiometry, it really is just doing stoichiometry and combining it with the ideal gas law. It really is just using both of those things in conjunction with each other.